Okay, so in 16.8, which in your book comes before 16.9, but in this class, as I'm teaching it, comes after 16.9, we're going to take a look at Stokes' theorem. And Stokes' theorem is going to do for curl what divergence theorem did for divergence. It's going to tell us what this weird thing that we know how to calculate is actually measuring. Okay. So there's some important setup. I haven't even written the theorem on the board yet. I've just written the setup because there's stuff to talk about before we can state the theorem. So we're going to have S. It's going to be an oriented piecewise smooth surface. So it has an orientation. Okay. And then we're going to have C, which can be written in this very suggestive way. That looks like a partial derivative sign, but I'm putting it in front of the name of the surface. That actually means that it's the boundary of S. And that's going to be positively oriented. I should probably have said positively oriented with respect to S. Now I need to define what that means, okay? Because we've talked about curves having an orientation, and we've talked about surfaces having an orientation, but we haven't talked about sort of putting those together to make them match up. Okay, so here's what's going on. So here I have a surface, okay, it's just a portion of a plane, and an orientation would be a choice of which of these two normal directions is considered the positive direction. So let's say I go with the upward direction as the positive direction. So that's like saying that this is the positive side of the surface, and the bottom side would be the negative side of the surface. Now, there are a couple of different ways that one can think about how to orient the boundary curve. Now, the boundary curve would just be this curve going along around the outside. So that's just this. It would almost be a rectangle except for the little tab there. Okay, so that's a piecewise smooth boundary curve that we have there. And I know that could be oriented so that we're going around it this way, or oriented so that we're going around it this way. Okay. Now, usually I have a little stuffed bear named Coffee Cup who likes to help me to illustrate how we can do the orientation of the boundary curve with respect to the orientation for the surface. Unfortunately, Coffee Cup got left at school when the campus closed, but I have my friend Brett who's going to help out. Now, Brett is wearing a scarf, and we mustn't laugh at him because he's very fond of this scarf. Okay, my mother made him this scarf to keep him warm. She didn't remember quite how small he was, and then it stretched over time. So it looks a little silly. But what I'm going to do is I'm going to rig it so that the scarf is on his left side right now. Okay, and you can see if he were walking around the boundary this way, then the surface lies on the side where the scarf is. It lies to the left. Whereas if he were to turn around and walk around this way, now the surface is on his right. Okay? Well, it turns out that the positive orientation for the boundary surface is if, when you're walking around the boundary, the surface is to your left. Okay? So this would be the positive orientation here. Okay? All right, so we've got that. Now, there's another way, in case you don't have a stuffed bear handy who's willing to walk around surfaces for you, you can also use the right hand rule. For the right hand rule, you take your right hand, okay? You take it and you curl your fingers around in the direction that you're walking around the curve. So if I'm walking around this way, which we said was the positive direction, I do this. Notice my thumb is pointing up. So my thumb points in the positive direction. Okay. If I tried to go the other way, so if I tried to go around this way, well, the fingers of my hand don't bend that way. This test really doesn't work well if you're double jointed. Then you just need a bear. Okay. But if I try to go around that way, I have to turn my hand upside down in order to make my fingers curve around things this way. And then that would be the positive orientation if I had oriented my surface downward instead. Okay, so that's what we mean by positively oriented with respect to S. So a positive orientation is not necessarily going to be upward or downward or leftward or rightward. It's going to be when I use my right hand to go in that direction for the curve, my thumb of my right hand points in the normal direction for the surface. Okay, and then we're going to have a vector field, and the niceness condition on that is that the component functions have to have continuous first partials at and near S, so in some open region containing S. And then what the divergence theorem says is that the work integral around C, so the integral of f dotted with t ds. Now notice, if this is the boundary of some surface, it's going to be a closed curve. Okay. I can't have a curve like so that's the boundary of any region. In order to be a boundary, it has to come back, and its ending point has to be its starting point, and so it will be a closed curve over which I'm integrating. Okay. So if I calculate this work integral, I could instead calculate it as a double integral, a surface integral, over the enclosed surface. And what I would be integrating then would be the curl of f dotted with n ds. So that is Stokes' theorem, that instead of doing this line integral over the boundary of a surface, I can instead do this double integral over the surface. And be careful, it's not just a curl of f, because that would be a vector valued function. I dot that with the normal vector to get a real valued function as my integrand. Okay. So we'll be taking a look at several examples in a moment. Just want to make one note about the types of surfaces that we're working with. They're going to be totally different from the types of surfaces we were just working with for the divergence theorem. Because for the divergence theorem, my surface had to be the boundary of the enclosed solid. So I could have something like the sphere, which completely encloses the solid ball of the same radius. Okay? But this surface doesn't have a boundary curve because it closes back on itself. Okay? I could have, for Stokes' theorem, I could have a portion of a cone, something like so. Now, that does have a boundary curve. That would be the curve, this circle here, where I'm cutting off the cone. I would not have seen this surface for divergence theorem because this doesn't fully enclose a solid. If I were to fill this with water, well, the water would pour straight through it because it's made out of paper. But if I were to waterproof the paper and then fill it with water and then turn it upside down, the water would fall out. So either way, the floor is going to be wet, so I'm not going to do this. But this doesn't fully enclose it. When we're working with the divergence theorem, if I want to have this, I could have this as part of my surface, but I would have to cap it so that it fully enclosed the solid region inside of it. Once I do that, it doesn't have a boundary curve anymore. Okay. So the types of surfaces that we're going to be using for Stokes' theorem are surfaces that are specifically not boundaries of finite solids, whereas the types of surfaces we used for divergence theorem must be boundaries of finite solids. Okay, so that gives us the statement of our theorem. In the next video, we will actually do a couple examples. Well, probably not a couple in one video, but we'll start working with it.